last time, so I rewrote the initial expression of what we have to compute and computed the expectation part. So something like, in this video I do some Fourier analysis on the bump function chi, and as a result we will get some description of the quantity to compute as an Euler product. I mean a product indexed by primes. So Fourier transform. Let chi be the Fourier transform of the following function. So this is not the Fourier transform of chi, but this function multiplied by exponential function. But I use chi hat because it's easier to write. So there are some ways to define the Fourier transform and the inverse transform, I mean the coefficients, but I normalize it so that the following holds. Therefore, by dividing by Ex, and we will use something like this. So I mean, since e to the power of this thing is, I mean, of course this part is the norm itself, so this thing becomes right. So I copy this expression here and I substitute this into the expression we had. This is the expression we had. And here we have chi. So I rewrite this thing. Note that I have changed the notation so that I use German A for ideals, not German B. What shall we do now? We want to exchange this sum and integral. It turns out it's convenient to replace the domain of integration by a bounded integral. So we want to replace the real line by this finite but rather long interval. Let me see. To justify it, of course we would like to know that this integral, with a being some ideal, and this finite integral are not so different. Yeah, basically this will be true because this Fourier transform is the Fourier transform of a compact support function. So it is a rapidly decaying function. So this difference is of course the integral on the real line outside the interval, and I can put the normal part outside, and I will discard the imaginary power because this is a complex number of absolute value 1. So specifically the rapid decay of this function for us means this is smaller than any polynomial decay. Positive large value up to maybe constant, depending on the exponent and the function in question. This implies that this part has exponential decay, arbitrarily fast exponential decay with respect to this log r. So this is smaller in size than any negative power of log r. Yeah, this somehow shows that we can exchange this r by this bounded interval up to an admissible error, but that fact is a little bit complicated to explain, so yeah, let's assume that it's fine. So we can replace the domain of integration. So now if we want to exchange a sum and an integral, so infinite sum of an integral on a finite domain, one way to justify such an operation is to check that this infinite sum it converges absolutely and uniformly. In our case, this amounts to checking that the sum over ideals here we have to show the convergence of this sum. I dropped the Möbius function because it is 1 or minus 1 if your ideal is square free. And we are considering the absolute convergence, I have dropped it. And now we are assuming that our ideals are all square free. And also this guy is not irrelevant when we take the sum, and this is a continuous function on the bounded interval, so we can ignore this. And let's recall that this guy decomposes into the p parts, where this condition here now depends on the p part. By which I mean I consider the same tuple, but I take the p part everywhere. So p part. Yeah, this means that our function here and here are both multiplicative with respect to the decomposition into p parts. So we can decompose the sum into the product of partial sums. So such that for all prime ideals, dividing some of the members is over the fixed prime number p. Over p means your prime ideal contains the integer p. But in this circumstance, this guy had been computed explicitly last time. Yeah, so there are several cases. First, if the ideals are all unit ideal, then the summand is 1. So next, yeah, the second simplest case is when these two ideals are both the unit ideal if the index or I is not fixed I0, and if for one the special thing it is a prime ideal, then yeah, I should be taking the product here. In this case, this is explicitly computable. Yeah, so this is not enough. So I have to distinguish two cases, at least two. So yeah, there are two possibilities, maybe three. So it could be true that both of them are the German P, or one of them could be the unit ideal. So depending on it, so in the first case I get in this case. In the second case, of course these are
norm of p to the power of minus 1 plus r inverse or minus 1 plus
the other cases. These other cases we will have. It's enough only to know that the quantity in question is at most 1 over p squared. I mean, because if the above cases fail, it is true either that this fails, namely this ideal is a proper ideal for at least two indices I. Then last time I showed that this expectation is at most p squared. So it will be even smaller because I have this factor. And it could be true that this first condition is true, but the second fails. So it means that your so the last time I showed under the first assumption that this expectation will be the inverse of the norm of this ideal, and if this ideal fails to be a prime ideal, or even if it is a prime ideal, if the prime ideal has a large norm, then the norm of this guy is at least p squared. So it follows that your average is at most p 1 over p squared. So you know this.